Soldering is a fundamental skill that any modeller making metal kits or scratch building will use, yet it is one which causes great anxiety and frustration, not helped by people continually telling you it is difficult or a mysterious black art. The more we're told things, the more we tend to believe them and the more anxious we become, because we lack understanding, experience, or both. I believe it's important to understand the process, not blindly follow what we're told. When we understand what is going on, we're in a position to make decisions to adjust what we do and make the process do what we require, and so construct better models. Materials, tools, and knowledge have evolved over the years, and as a result, so have techniques. I've deliberately laid out soldering from the basics, so I hope it will help the less experienced modelers to understand soldering better and be a useful reminder to the more experienced. A lot has been written and said about soldering over the years, with many do's and don'ts, some of which are important, others less so and may be discarded. Which is which are for you to decide, but before you do, I encourage you to challenge what you hear and, unless it is obviously reckless or dangerous, experiment in order to find out for yourself what works for you. What is soldering? Well, it's a process whereby metal parts are joined together using another metal which has a lower melting point. We rarely use pure metals in our hobby. Brass, nickel, silver and white metal, the three commonest construction metals that we use, are all alloys. An alloy is a mixture of two or more metals in various proportions to promote particular properties. Solder is also an alloy. Brass is an alloy of copper and zinc, roughly in the proportion of 2 to 1. Sometimes small amounts of other metals are included to impart particular properties, and its melting point is around about 930–950 degrees Celsius. Nickel-silver is an alloy of copper, zinc and nickel, the latter giving the silver colour. It's harder than brass, has a higher melting point of around about 1040 degrees Celsius. White metal is principally of lead and tin, but may contain substances like cadmium, bismuth and zinc. It's fairly soft, much softer than either brass or nickel-silver, with a much lower melting point at around about 180 degrees Celsius. All three alloys and the solder will conduct electricity. Our fourth alloy is solder, which, like white metal, is based on lead and tin, which makes it soft with a low melting point. The tin content varies from 5 to 70%. This alters the melting point, which is typically between 70 and 450 degrees Celsius. In our hobby, common melting point solders are 70, which is low melt solder, 100, which is good for joining white metal to brass and nickel-silver, 145, 179 and 183. Other metals, for example silver, are sometimes incorporated to tweak the properties, and some less healthy elements occur naturally with lead and tin as impurities, which are costly to remove. This is important to remember, as the hobby still uses lead-based solders in the main. Solder commonly comes as round wire on a spool, but can also be bought in a bar and as a cream. In recent years, the poisonous nature of lead has been taken more seriously, and lead-free solders have been developed for a range of applications, with the lead being replaced by metals such as tin, copper, silver, bismuth, indium, zinc, antimony and manganese in a variety of proportions. They're not as easy to use in modelling and have a melting point usually in excess of 210 degrees Celsius, which is why we still use the lead-based solders. Soldering above 450 degrees Celsius is called silver or hard soldering, also known as brazing, and to get that high temperature we must employ a flame. It's beyond the use of our ordinary soldering irons. Hard solders with the highest melting points are usually an alloy of copper, zinc and silver, with small amounts of other elements, again to adjust the properties. In this presentation I'm not going to deal with silver soldering. The chemistry involved is very wide-ranging, which I'm sure you'll be very pleased to know we're not going to go into any further. Flux is a chemical used with solder which cleans the metal, helping the solder to flow and penetrate a joint. When metals are heated in air, they combine with oxygen to form oxides on their surface, which are a barrier to a good bond. Flux is a reducing agent. It reduces those oxides, putting more of the metal back into the joint, and that joint stronger and a better conductor of electricity. Many substances can be used as a flux, but there are two main types. active or acid fluxes, and passive or rosin fluxes. A flux which is good in one situation can be hopeless in another. Rosin fluxes are better for electrical work. It therefore follows that there is no universal flux, though in modelling a wide range of fluxes is rarely needed anyway. I use the same acid flux with brass, nickel silver and white metal, and a different one, a rosin-based one, for electrical soldering. Fluxes may be liquid, paste or even solid. If you can, see if you can try a range of your friends' fluxes and see what works best for you. A flux commonly used in modelling is dilute phosphoric acid, usually around about the 10% dilution. But people also use hydrochloric acid, zinc chloride, ammonium chloride, sodium carbonate, charcoal and lime. I also know people who have used Coca-Cola. When I was in the USA a couple of years ago, I spent time chatting to a tinsmith who was using powdered pine resin. Borax is a common flux for silver soldering. Some solders have flux incorporated in them, for example, multicore solder for electrical work. This demonstration shows how important fluxing and clean metal are. The piece of scrap etch has been handled a lot and picked up dirt and grease from my fingers. When I work some flux over an area, you can see the flux cleaning it and the colour changes. Now I'll put some solder on the fluxed area, then to the part which was not fluxed. The solder puddles and doesn't stick to the brass at all well. Commercial brands you might see on a modeller's bench include Fluxite, Friolux, Powerflow, Baker's Fluid, Templar's Telux, Easy Flow and the Cars range. Ask modelers about their choices, as each has its good or bad points. Nialatin and Friolux are solder paints which come with the flux already mixed in. Ursin Multicore is an electrical solder with resin flux incorporated into cores within the solder wire. Virtually all fluxes leave a residue of some sort, and that residue needs cleaning off your model regularly and thoroughly, especially before you paint. We can apply our flux in a variety of ways. These are a few, but first, if you use a liquid flux, I suggest you decant some into a smaller container and keep the larger stock bottle somewhere safer. A common way to apply flux is with small brushes. These work well, but the flux does tend to attack the glue that holds the bristles, then they drop out. Brushes usually go along with bottles, so consider making a secure base for your bottle to stop it getting knocked over. You could use plastic card and tube, or even a block of wood. A bottle with a broad base relative to its height will be more stable. My own preference is for a 2 milliliter syringe with a fine, blunted hypodermic needle. The needle will last a lifetime, but the plunger in the syringe eventually gets a bit sticky. New syringes, though, are cheap, a matter of pennies. You can buy bottles that take those hypodermic needles. Paste flux you can apply with a cocktail stick or a coffee stirrer, as you can solder paint. Some modelers will use a brush, but that can get a bit bunged up. I mentioned earlier that there were impurities with lead, and that lead itself is poisonous, so before we move on from these consumable materials, I will raise the subject of health and safety. All too often it is sneered at. Here we go again. But when soldering, it is important for you to realise that you are dealing with hazardous substances. The risks may not appear major, but they are risks all the same, and you should take steps to minimise them. White metal and solders contain lead and other toxic substances, so don't lick your fingers or eat whilst you're handling these materials. Wash your hands thoroughly when you've finished and before eating. Heat will boil flux and release fumes, so again, don't solder with your head close to the work. Make sure you have adequate ventilation to remove those fumes. Some modelers rig up a computer fan to blow air across their work whilst they're soldering. It is quite possible to overcook solder and release nasty fumes, so don't just wind your iron up to the maximum heat. I'll have more to say about setting the correct temperature later. Our skin doesn't handle heat well, so your soldering iron needs to be put down somewhere safely where it won't burn you, your bench or instruction sheets, and it can't fall onto the floor or into your lap. If you must use fingers to hold parts, consider protecting them with some sort of pad, a bit of cardboard, or even those little rubber fingertips you can buy from stationers. Use something to hold your model or the parts if you can, like a vise or tweezers. Your eyes are precious, you only have the one pair. Flux can spit, so consider wearing eye protection even if it is only a pair of specs. Above all, try and keep your work area clean and tidy. I'm sure you can think of other hazards and will take appropriate steps to deal with them. Now we'll move on from the consumable part of the hobby to the equipment. My first experience with soldering was with my father, and his soldering iron was a big lump of pointed copper on a metal shaft, and it had a wooden handle, which he heated on the gas cooker. In those days, one just used plenty of heat, and he controlled his iron by looking at the colour of that copper tip, waiting for it to glow red hot. Plumbers commonly used, and some still do, blow torches. Sometimes there can be dire consequences. A safer method uses resistance soldering. Blow torches, portable or connected to a gas supply, are still used in jewellery making. In model making, they are used if silver or hard soldering and brazing. For modellers, the electric soldering iron has been a boon. Early types were a little crude, but with the development of plastic they got better. The gun type gives quick heat at the tip when you press the trigger, but it's not so controllable and has limited use in railway modelling. In recent years, the temperature-controlled soldering station has become common. One of my best investments was one of these, as it gives me much more control over the process of soldering. With them, temperature is controlled with a dial or buttons and is fairly precise, which is very useful because solder can be overheated, releasing nasty fumes, and with white metal you work very close to the melting point of the metal. They normally come with a stand for the hot iron together with a sponge or brass swarf ball to clean your bits. A silicon cable on the iron is more flexible and much nicer to use. Even more recently, temperature control has become incorporated into the handpiece, and there are cordless, gas-powered irons which can use a small flame to heat the tip. They can be very useful where a power supply is not to hand, for example under baseboards for electrical work and repair at exhibitions. Most soldering irons these days have interchangeable tips for the range of shapes and sizes. This is very useful, as we'll see a little later. A stand for your iron is essential. If you buy a soldering station, one usually comes with it. As part of that stand will be a holder for a sponge or a ball of brass swarf, both of which are used to wipe your bit clean from time to time. The sponge should be damp, so I also keep a small bottle of water on my bench. The last piece of equipment I'll mention is resistance soldering. It's a different method of soldering using electrical resistance to generate heat in the solder joint. It's quick, heat is very local, heating and cooling is also quick. A big plus is that you hold your work in place before, during and after soldering whilst the solder cools, because the heat is only applied with a foot pedal when you complete the circuit. You'll find my presentation on resistance soldering in the Scaleforce Society's YouTube channel, and details of how to find it are on the accompanying sheet. Now to the nitty-gritty. We'll move on to look at what happens when you solder something. This means using some more technical words. Words we use a lot when we're talking about soldering are heat, temperature, and to a lesser extent, energy. But what exactly are they? We'll start with energy. The word comes from ancient Greek through the Latin word energia, which refers to activity. Energy makes things happen, and to cut a very long scientific story short, energy comes in a variety of forms, more than a dozen, of which we are concerned here with thermal or heat energy. When we're low on energy, we get tired and snooze and our body temperature drops a bit. During the day, after a few hours of modelling at the bench, our energy levels also drop and we need to refuel, top them up with afternoon tea and a bit of cake. After that, loads more energy, we're ready for another session creating wonderful models. Our energy comes from food. It's no accident that the more active we are, the warmer we become. Any activity generates heat, which brings us to temperature. Temperature is just a measure of hotness and coldness, but it is related to the amount of energy. There are several temperature scales. Photographers amongst you will be familiar with the Kelvin scale. In our everyday lives, though, in the UK, we use the Celsius or centigrade scale. Older modelers, and those in the USA in particular, will be familiar with the Fahrenheit scale. I'm sorry, we seem to have a problem. Whilst we fix it, we'll play you a little music.
The second law of thermodynamics. Heat cannot of itself pass from one body to a hotter body.
Heat cannot of itself pass from one body to a hotter body.
Heat won't pass from a cooler to a hotter.
Heat won't pass from a cooler to a hotter.
You can try it if you like, but you'd far better not.
You can try it if you like, but you're far better not.
Cause the cold in the cooler will get hotter as a ruler.
Cause the cold in the cooler will get hotter as a ruler.
Because the hotter body's heat will pass to the cooler.
Cause the hotter body's heat will pass to the cooler.
Heat is work and work is heat and work is heat and heat is...
Welcome back. I hope you were suitably entertained. Now let's get back to the matter in hand. There is a scientific law which says energy cannot be made or destroyed. It just gets changed from one form to another. In our soldering irons, electrical energy is converted into heat or thermal energy, the amount of which is measured as temperature. By setting the temperature to, let's say, 200 degrees Celsius, we limit the amount of energy in our soldering iron, and by limiting the energy, we keep the heat level down where we want it. This is useful when soldering white metal, of which we'll learn a bit more shortly. Raise the temperature setting to 300 degrees Celsius, and we allow more energy into the iron, and the heat increases further. We have more at our disposal. We're now getting into the realms of soldering harder metals like brass and nickel silver. Raise the temperature to 400 degrees Celsius and we're getting close to the upper limit of our iron's capacity for energy and heat. We need this level of heat in order to use the higher melting point solders efficiently. I referred earlier to setting the correct temperature for your solder. It is not good practice to simply wind the iron up to maximum and plough on. You may get things to solder, but you may also have poorer, weaker joints as solder, especially that with the lower melting point, can get to its boiling point when you then get small bubbles of air into the joint. You can also denature the solder and release unpleasant substances into the air that you are breathing. Conversely, if the temperature is set too low, you will have difficulty getting your work hot enough for the solder to melt properly and form a reliable joint. I was told some time ago, and found very useful since, a rule of thumb guide which is to double the melting point of the solder and add 25 or 30 degrees to give you the temperature you should set your iron at. So, for low melt solder with a melting point of 70 degrees Celsius, double is 140, add 30, that gives you 170 degrees Celsius. For 145 degree solder, we come out at 320 degrees Celsius. For higher melting 179 degrees solder, we would set our iron at around about 388 degrees. These, though, are simply the starting points. It gives you a ballpark figure. Now we come to the different tip size. Tip shape you can match to your work and have your own preferences, but the tip size can be important. A smaller tip is made of less metal and therefore it can hold less heat at any given temperature. This means you could set the temperature at 200 degrees Celsius and solder white metal, something I regularly do. A larger bit has a lot more metal in it, so at the same temperature it will hold a lot more heat. So you'll be advised to reduce the temperature setting and the amount of heat to nearer the calculated 170 degrees Celsius. Now let's look at heat transfer and what actually happens when we solder a joint. I will use white metal as an example because it illustrates things perfectly well, and I'm aware that white metal causes more anxiety because of the fear of melting the casting. But what follows applies equally well to soldering any metal. We'll use the same two bits that were in the previous slide and begin with the couple of heftier castings of a van side and end, which we will solder together. The temperature I'm going to leave throughout at 200 degrees Celsius. We heard earlier a snatch of Michael Flanders and Donald Swan referring to the second law of thermodynamics. Heat won't pass from the cooler to the hotter. You can try it if you like, but you'd far better not, because the cold in the cooler will get hotter as a rule, because the hotter body's heat will pass to the cooler. Heat from the hot iron passes to the cooler metal that you're going to work on, making it get hotter. As a result, the iron will get cooler. Because of the temperature difference, the metal is at room temperature, say 20 degrees Celsius. The heat transfer is rapid, and as the casting warms up, the bit temperature goes down as the heat is transferred. With a smaller bit, which holds less heat, it'll take a long time for the metal at the joint to heat up. In fact, with these castings, it may not even get hot enough to make a decent joint. With the larger bit, which holds a lot more heat, heat transfer is much more rapid and the temperature of the casting rises more quickly to make a good joint. However, as the casting is quite large, there is a lot of metal which can absorb a lot of heat, so it's unlikely you would get the metal hot enough in the time it takes to solder the joint to get the metal up to the 180 degrees at which white metal melts. So, we see that the smaller bit cannot supply enough heat to do the job, but the larger bit can. Even though the larger bit is set at 200 degrees Celsius, above the melting point of the white metal, it is most unlikely to warm the castings anywhere near that melting point in the time it takes to solder the joint. This time, we'll use the more delicate castings of this timber wagon and solder a couple of stays to the central pole. The temperature is still at 200 degrees Celsius for both bits and the wagon is at room temperature. The same heat transfer takes place as it did on the previous slide. With the smaller bit, again, heat transfer is fast and the bit cools as the heat passes to the casting, but as the bit holds less heat, the casting will not heat up as fast as it will with the larger bit. Here, there is a shed load of heat in the bit which, when put to the casting, floods across and the casting heats up rapidly to its melting point because there is little metal to absorb so much heat. In this situation, the smaller bit is best as you are less likely to melt the casting in the time it takes to make the joint. But with the larger bit, the casting heats rapidly to its melting point and you end up with a blob of white metal. The solution? If you must use a large bit for soldering these delicate bits of white metal, reduce the temperature and hence the amount of heat that bit will have. You saw this a few slides ago. Electrical energy is converted in the soldering iron to heat, which then passes through the solder to our workpiece. If you look closely at your iron, you will most probably see some writing which, apart from the maker's name and the voltage of the iron, has a number followed by the letter W. W refers to watts, which in turn tells you the power of the iron. This is a measure of how quickly the iron can replace that heat lost from the tip. So the more watts on an iron means your iron is more powerful. With more watts, you have more power in reserve, and the heat that passes out from the tip of the bit is replaced better. In turn, the bit will cool more slowly and the temperature will stay nearer to that you have set. It's important to understand that a higher wattage does not mean that the iron gets hotter. It stays near that set temperature for longer. It would seem then that we might just as well have an iron with a high power rating, but this may not be desirable. For electrical work, because the components are generally small and therefore heat up quickly, if the iron is too powerful, it may well fry those components, so a 12 to 25 watt iron is safer and usually ample. For kit building, you're soldering a larger amount of metal which has to be heated up to get a good soldered joint. A more powerful iron, therefore, is needed, or the iron will be struggling, and a minimum of 50 watts is recommended for 4mm modelling. If you work in 7mm scale or greater, then you will have even more metal to heat, and so a more powerful iron of at least 60-75 watts is suggested. That's the minimum. I know some heavy modellers who use irons that are a lot more powerful than that. You should now have a better understanding of the materials you work with, together with the equipment and the hazards you might encounter. We've gone a bit deeper into the subject, and I hope you now have a better understanding of what actually goes on when you solder items together. Before looking at a few specific soldering techniques, there are some basic requirements for successful soldering. The work must be clean, free of dirt, grease and the oxide coating. You can use a file, fine abrasives like wet and dry or micromesh, metal wool. You can even try washing it in mild acid or alkali. Time spent preparing the metal is invariably time well spent. Use an appropriate temperature setting so that you have plenty of heat. Is your iron powerful enough to maintain the tip temperature? Is your bit of an appropriate size? Keep the tip of the iron clean. Flux well, but don't overdo it. All fluxes will need cleaning off regularly, usually after each session is sufficient. Both sides of the joint need to be hot for the solder to form a good bond. The strength of a joint is in the alloy formed between the solder and the brass or whatever metal it is. Solder itself is actually weak, so the thinner the solder is in the middle, the better the joint should be if you have used sufficient heat to form that solder metal alloy. Try and cut down on the amount of solder that you use. Cost a part of wasted solder. If you have to clean solder off, then it's valuable modelling time lost. Use progressively less and less solder as you work until you find that ideal amount which gives you a good joint. Wherever possible, solder from the back or inside your work wherever it does not show. Now we'll look at one or two specific techniques, and we'll begin by looking at tinning. Tinning involves covering something with a thin coating of solder. The term itself comes from coating thin steel or iron with tin to prevent rust. Tin cans are the example. We use tinning in model building in two ways: on our soldering iron bits and on the parts that we want to solder together. Why? For protection and efficiency. A thin coating of solder, which remember contains a lot of tin, protects the bit on your iron, especially from acid fluxes, so that the bit will last longer. It also improves heat transfer, helping the solder to melt more easily. Let's begin with the bit on your iron. There are many guides on how to do this on the internet, but very quickly, clean the bit, take off the old solder and dirt. Even if it's new, give it a good wipe. Do not use a file or abrasive because that will damage any coating that there is on the bit. Use a damp sponge or a cloth or even a tip cleaner. If you've not already done so, turn the iron on so that it is quite hot, and then put on a generous amount of solder and make sure that the tip is covered. Leave it on for a short while before wiping off the excess solder, just leaving a thin layer over the end of your bit. You should now have a shiny layer of solder. You may need to repeat the process if it's not taken properly. Keep an eye on your bit. When it becomes dirty, the solder will not flow as well, so clean it and re-tin. You can buy proprietary tip tinners and cleaners, which will make the job simpler. These are a mixture of powdered solder and flux that you dip your cleaned bit into. We'll look at tinning parts of your kit like an overlay. Whenever you solder, the parts must be clean, which means removing dirt, oxidized metal, finger marks, old sellotape, glue, whatever else there is on your etching. I find these sponge sticks of micromesh very useful. You can see where I've cleaned half the back of the overlay. You can even wipe the metal with IPA. Double diamond might work wonders, but not beer. Next, flux the part very thoroughly, making sure that the whole overlay has been covered. Don't just show the flux to the part, work it over the surface. Remember that that flux will also clean the metal. Use a flat bit and add a thin layer of solder. You don't need much solder, so it may take a few goes to find how much, or rather how little, you need. If in doubt, underdo the solder to start with, as it's easier to add more than to remove the excess. Where the iron is lifted off, there will always be a thicker patch of solder. Run the iron off the overlay and onto the edge of the fret. Solder will follow the heat, so you can drag the excess solder here onto the edge of the fret and not have to clean it off. To do the job properly, you should also clean and tin where the overlay is going, in this case the sol bar. It's then a case of cutting the parts out, putting them together with a little bit of flux between them. Lastly, you apply heat. You can do this with either a large clean bit or, as I prefer, using resistance soldering. However you do it, start in the middle and work towards the edges because the overlay will expand when it is heated. Don't rush it, take your time. A short demonstration. These are overlays for sol bars. Etches are often made from 12 thou brass and overlays half etched, so typically 5 or 6 thou. These are already fluxed. See how they buckle when heated because the ends are fixed to the fret. Remember this when you attach the overlays to your kit. Begin in the middle and work towards the end. I always try to tin on the fret so I can run the iron onto the edge to take off surplus solder. It also makes holding a lot easier. Step soldering uses several solders that have different melting points. We do this to prevent remelting of already soldered joints. Solders are used in descending order of melting temperature so that the joints previously soldered are not undone. It also means, of course, that you have to reduce the temperature of your iron each time you make a joint. When you're soldering brass to brass, you might begin with a high melting point solder, maybe as high as 221. Then you would use 179 before coming down further to 145. Each time you reduce the temperature of your iron. These backheads are from DJH kits, and you can see here a lot of soldering of brass parts quite close together. However, at the simplest level of using step soldering, you're attaching the brass to the white metal of the backhead. And if you use 100 degrees solder, you won't unsolder the brass to brass work, which is most probably being done at 145 or 179 degrees Celsius. Joining white metal to brass can be problematic because low melt solder does not form a particularly good bond with either brass or nickel silver. What you need is an intermediate layer which is done by tinning the brass with a higher melting point solder, for example 145. You then solder the white metal component on with the low melt solder, and that low melt solder then bonds to the 145 degree solder rather than the brass. More recently, a newer solder with a melting point of 100 degrees Celsius has been developed, and this does bond better with the brass and nickel silver, so it does away with the need to tin the hard metal first. In other words, you can solder white metal to brass in one go. Here's a way of putting your knowledge of heat transfer to good use. Soldering a bit of brass wire into a hole in white metal, for example adding handrails. Drill a hole that's slightly larger than the diameter of your wire and tin the end of the wire with 100 degree solder. Put a drop of flux on the hole and then put the wire in. Ideally, it should be a nice snug fit. Use a clean, hot iron set at around about 300 degrees Celsius, maybe a little bit higher, but not too large a bit. Put the bit on the brass wire near where it goes into the hole and let the heat pass down the wire to melt the solder in the hole. You may just see the solder melt, a little flash of silver in the hole, in which case take your iron away, let the wire cool, and the job is done. With luck, no, let's now call it skill. There will be no cleaning up to be done. When I solder white metal, especially delicate pieces, I use a pointed bit, usually set at 200 degrees Celsius, only reducing the temperature if the parts are very, very small. I've repaired delicate pieces like this gas lamp where the supports are barely 0.6 millimeters in diameter. There's little metal here to absorb heat, so I must be quick with the iron. Having done this sort of thing many times, I'm confident with the iron at 200 degrees Celsius, but you might prefer to drop the temperature to about 170 degrees Celsius for your first goes. Wipe the tip of your soldering iron clean, no tinning, and get a very small rhino horn of solder onto the tip. If this is difficult, cut a small piece of solder and then pick that up with the soldering iron. Next, put the white metal in position, add a drop of flux and touch the solder, not the iron, to the join. Don't let the iron touch the white metal. The solder will go into the joint. The heat flows through the solder into the white metal and takes the solder with it. As soon as this happens, take the iron away and the job is done. You need very, very little solder. There are times when we have to solder very small, delicate pieces or need to put only very small amounts of solder onto something, for example when we're making moving parts. For this I use a pointed bit, but find a tinned bit has too much solder on it, so I wipe the bit clean. I then limit the amount of solder on the bit by cutting pieces off the stock. I actually keep a small pot on my bench which has small pieces in. If necessary, I'll cut a piece in half, and half again, and even half again, using tweezers and a scalpel. I mended the gas lamps by picking up a small piece of solder with a clean bit. You can also make very thin solder and cut it into small pieces with a scalpel. Either load your iron with a good blob of solder, then throw the solder on the bench, or, if you have access to any, pass a length of the solder through a jeweller's rollers to make a thin foil. Jeweller's rollers are needed to apply enough pressure. Those for rolling brass parts are not good enough for this. Moving parts are another aspect which invoke fear. Fear of soldering everything up solid, so it makes sense then to put only a small amount of solder on in the first place. Assemble the pieces and add a drop of flux. Don't flood the work. Pick up a small piece of solder on your iron and put it precisely where you want it. More often than not, the amount of solder needed is very small. Anyway, it's always easier to add another bit than to take off the excess. If a moving part does get soldered up, hold one part in a vise, heat the joint and waggle the other part when the solder melts. Take the iron away, but keep waggling until the solder has set. This should solve the problem. If you've used too much solder, you will have to take it apart and clean and try again. There it is, soldering. I hope you found something useful here to use in your modelling. I suggest you have a range of solders, low melt, 100, 145 and about 180, together with 3 or 4 different sized and shaped bits for your iron. Make sure your iron is powerful enough, and if you've not got one already, consider a temperature controlled setup. Clean the metal you're soldering. This is very important. Flux thoroughly and use plenty of heat, but don't just wind the temperature up. Picture what happens with heat transfer and balance the bit size with temperature. Challenge what you're told, including what is in this presentation, by experimenting and finding out for yourself what works and what does not. Develop your own technique and then practice. Your scrap metal is a valuable resource, not just there to make extra bits for your kits, but to practice on. So don't simply throw it away, use it to test out ideas. Happy soldering, and may your models get better and better. Goodbye.